So today we are going to look at some questions in MyLab Math about section 1.1 and 1.2. I received one email only so far about the homework, so we want to look at it together. Let me share. You can see it, right? This is a question from section 1.1. Let's follow the description of the question, one step at a time. Repeat the following procedure for the four given numbers. The procedure is multiply the number by 10, add 12 to the product, divide the sum by 2, subtract 6 from the quotient. So the procedure has the following steps. Step 1, step 2, step 3, and step 4, right? So let's do the first number first. The first number that is given is 1. So we multiply 1 by 10. 1 times 10. We have 10, right? So that's the first step. Second step, add 12 to the product. So add 12 to 10. 10 plus 12 gives us 22. Second step. Third step, divide the sum. The sum is 22 by 2. So divide 22 by 2. We have 11. Step 4, subtract 6 from the quotient. The quotient we just got is 11. So we are going to use 11 to subtract 6. Subtract 6 from 11 is the same with use 11 to minus 6. We get a 5. Right? The answer is 5. So we have the first cell taken care of. Second number, excuse me. Second number that is given is 6. We do the same thing with earlier. First step is multiply by 10. We have 6 as the product. Second step is to add 12 on top of the product. So 6 plus 12 equals 72. And then we divided the product 72 by 2, cut it in half. 36. And then use the quotient 36 to minus 6. We have 30. So we have the second cell. So far, it's totally doable, right? And the third number we are given is 8. We do the same thing. Apply the procedure, the 4 steps. First step is to multiply the number 8 by 10. We have 80. Let's see if I received a message. No. Oh, left, lane left. So I'm going to mark the attendance around 10 minutes every class. So we have 6 more minutes. I'm going to continue from here. And the second step is to add 12 on top of 80. That gives us 92. Third step, divide product 92 by 2. That gives us 46. And then use 46, the quotient, to minus 6. We have 40. That's the message sound, right? I'm having trouble viewing the content. Can I leave the group and rejoin to see if that helps? Please let me know, other classmates, do you see my contents? Do you hear me well? Okay, then yes, Lauren, try that. Okay, awesome. Thank you for your response. And the fourth number that is given is 11. So we multiply 11 by 10. And we have 110. And add 12 on top of 110. We have 122. And divide 122 by 2. We have 61. And then use 61 to minus 6. We have 55. Right? So that takes care of the first 4 steps of this question. And part 8, write a conjecture that relates the result of the process to the original number selected. Represent the original number as n. So now we are actually, you know what? We are in induction. We are doing induction. We are applying the inductive reasoning from specific to general, right? Yeah, now we have 4 numbers. And we are going to use n to represent any number and any natural number here. So we have 1, we have 6, we have 8, we have 11, 4 cases. And then we are going to from specific to general. If we have number n, we multiply n by 10. We have 10 times n. It's supposed to be lowercase n. And then we add 12 on top of it. So we have 10n plus 12. Third step is to divide that by 2. Let me use the equation. We have divided by 2 equals, yeah. So the numerator is going to be 10n plus 12. Numerator has 2 terms, denominator has 1 term. So we use each term in the top divided by 2. We have 10n divided by 2 have 5n, and 12 divided by 2 have 6. That's the result after step 3. And then we are going to apply the last step of the process, the procedure. Use the quotient 5n plus 6 minus number 6. Positive 6 and negative 6 cancel each other, right? So we end up with 5n. So if the given number is n, we after the procedure, I don't see the new message though. After procedure, we end up with 5n. Okay, yeah. If we start from number n, after applying the procedure, we end up with 5 times n. So that's the reason your answer for part A is supposed to be 5n after you simplify your answer. That process so far is induction. Part B, represent the original number as n and use deductive reasoning to prove the conjecture in part A. Multiply the number by 10. So what happened here is, let's go back to the question here. Represent the original number as n and use deductive reasoning to prove the conjecture in part A. Multiply the number by 10, so we should have 10n here. you should enter 10n here. And continue. Add 12 to the product. So 10n plus 12. Divide the sum by 2. Divide 10n plus 12 by 2, we have 5n plus 6. And last step, subtract 6 from the quotient. 5n plus 6, and then minus 6, we have 5n. That's what the question wants. You use n in this process. Is that clear, guys? And that's one question. Yeah, so now let's go back. I'm going to log in my Pearson.
Oh my God.
You have any questions? In section 1.1, we have, I remember there are a few questions similar with that question, and that probably is the only challenging problem there. Nothing from me. Thank you. That helped a lot. Okay, no problem. And let me take a little bit of time to mark the attendance right now, okay? In Starfish. So we have Lauren, Aiden, Ashley, and Carly.
Oh my gosh.
So we have Braxton is absent. Natalia is absent today. And Leon left, so is still absent. All right. Awesome. So 1.01. It's quite slow, the internet. The questions I see on my end would be similar with yours, but not exactly the same. Sometimes they change the numbers. Okay, so this is about the order of operations, right? Yeah. Would you like to help me to process this question? I'll give you 1 minute and let me know what you have. Use the order of operations to simplify the expression. Yesterday, we have 3 rules about the correct order of operations, right? The first rule is PEMDAS, and second rule says if the expression only has additions and subtractions, we go from left to the right. The third rule says if the expression only has multiplication and divisions, we go from the left to the right. So this one we have subtraction, multiplication, addition, and let me know what do we do the first. Two times 2 first, awesome. That is okay. Yeah, exactly. So we're gonna process the multiplication first. multiplication first. So 2 times 3 is 4. And now we have 13 minus 4 plus 3, right? And then what do we do? Do we do the subtraction or addition? We do 13 minus 4 first, where we added 4 and 3 together first. Based on the rule number 2, we should do the subtraction first, right? 13 minus 4 gives us 9. 9 plus 3 is 12. You have the same thing? Okay. Evaluate the following expression for x equals 3. I'm going to do that question on my note. I think because we have so many windows open and also so many people, is pretty slow, to be honest. No reaction. Take snip. Okay, how about I'll just remember the question. 4x plus 15. All over 4x plus 15 in the numerator, denominator is 9x. And we are evaluating that for x equals 3. Okay, so this is a very good example, because through this example, I'm going to show you how do I plugging in. Okay, plugging in is a very important technique. So this is what I'm going to do. Since we're evaluating this expression for x equals 3, the value of the expression, the expression has a variable x. The value of the expression depends on the value of x. So in order to know the value of the expression for x equals 3, we have to substitute 3 for x in the expression, right? And we call the process plugging in. So this is how do I plug it in. I copy the expression first. I'm going to replace x with a 3, right? So I'm going to use the parentheses to hold a place for x, to frame x. And then I'm going to erase x from the parentheses. And then I'm going to put a 3, because we are evaluating the expression for x equals 3. I'm going to put a 3 in the parentheses. Please use this process. Use the parentheses. Sometimes we have negative numbers. You will see the benefit of using parentheses. Let's continue to evaluate or simplify the expression. The fraction bar here actually is a grouping symbol. It's a grouping symbol. How do we see the fraction bar here as a grouping symbol when it's supposed to be a division, right? Numerator, denominator. The fraction bar actually is a division operation. But you know, we are going to treat the fraction bar as grouping symbol because it separates the numerator and the denominator. Numerator, whatever on the top, that's a numerator. That's a numerator group. Whatever on the bottom, that's a denominator group. So that's the reason we see the fraction bar as grouping symbol. Remember PEMDAS? We should take care of whatever in the grouping symbol first, right? So let's take care of the numerator group. Take care of the numerator. Numerator has multiplication, has addition. So we do the multiplication first. 4 times 3, 12. Plus 15, we have 27. That's the numerator. Denominator, 9 times 3, 27. And then we process this division. 27 over 27 equals 1. That's the correct way to take care of this question. The value is 1. The number you see might be different from mine. Write the following phrase as a variable expression. Use x to represent a number. The sum of a number and 11. Anyone would help me to solve this problem? Are you guys still here? Pretty quiet today. Let me see, where are you guys? I don't mind some noises, you know. Delayed here. Okay, would it be x plus 11? Let's see. I think it is x plus 11. Sum of x and 11. Perfect. Thank you so much. So let's enter x plus 11. There we go. Yeah, those questions have nothing to do with, the questions earlier had nothing to do with induction deduction, right? It's just some foundation, basics from algebra. The statement, number 4, statement 3 plus 3 equals 6 serves as an what to the conjecture that the sum of two odd numbers is an odd number. Counterexample, all right? Yeah. The conjecture assume any two odd numbers add up to odd number. Let's see. For example, 3 and actually is a false statement, obviously. So we can easily find a counterexample. Yeah. 3 plus 3. 3 is odd. 3 is odd. Add up together, we got an even number. So this is a counterexample. Fill in the blank. Arriving at a specific conclusion from one or more general statement. So from specific, arriving at specific from general. So from general to specific, is this inductive or deductive reasoning? The number of examples increasing or decreasing? Hello? You know, we learn mathematics, you still need to have a certain level, good level of reading comprehension. Deduction, awesome, thank you. It is deduction. Common mistakes you see, specific first and then general. No, it means arrive at specific from general. So this is from general to specific is deduction. Awesome. Arriving at general from based on observations of specific examples, induction, increasing, right? From specific to general, increasing. Find a counterexample to show that the following statement is false. The statement is false because the following precedent is a counterexample. Select all that apply. What kind of statement this is? President. Oh, this is a statement. No U.S. president has been younger than 65 at the time of his inauguration. Use the table below. Yeah, this is a statement. I'm highlighting. Has no U.S. Okay, this is negation. No U.S. So Obviously, it's false, right? So we have a Roosevelt, Theodore is a counterexample. We have John Kennedy, counterexample. We have Obama, counterexample. Harry Truman is also counterexample. And all other three, they are older. Hold on. No president has been younger than. They are, yeah, the ones I checked have been younger than. Okay. And that's it. No singers appear in movies. We had this, right? Elvis Presley. Find a counterexample for the statement. If a number is multiplied by itself, the result is even. This one is a counterexample. 5 times 5 gives us an odd number. How many questions total? 26 questions. The sum of two 4-digit numbers is a 5-digit number. Find a counterexample. So we can try 1111. The sum of two 4-digit number 1111 is still a 4-digit number, right? Because the sum is 2222, it's still 4 digits. Adding the same number to both the numerator and the denominator does not change the fraction's value. This is so wrong. This is very wrong, okay? Yeah, please never do that. Please never do that. Choose the correct answer below. We can try this one. Yeah, is this one. So 1/2, the original number is 1/2. If we add a 1 to both top and bottom, we would have 2/3. Obviously, 2/3 is different from 1/2. This is very false, very wrong. If the difference between two numbers is odd, then the two numbers are both odd. Which is even, which is odd, but 8 and 3 are not both odd. Does this help for you to get started on your homework, guys? I want to make this class like customized. We only have a few students, right? Yeah, thank you. If you have any suggestion, I think because the most important thing is to do the homework. I think we can just do the homework together, at least some of them. Identify a pattern, okay? 2, 10, 8. So as you can see, from 2 to 10 is 8 more, right? Yeah. Add a 10.
42.
Yeah, you add a 8 to 34. 42. Awesome. That is arithmetic actually, because equal difference is 8. Very good. The only thing I was curious about was the worksheet. Do we print it out? Do the problems then email it back to you? Yesterday, I assigned one worksheet. Anybody remember which worksheet I assigned yesterday? Huh? The correct order of operations, right? Yeah, exactly. Yesterday, we went over the correct order of operations. We went over the worksheet. So far, the only worksheet you need to print out is that worksheet. Print it out and solve the questions and scan or take a picture of your work and email them to me, and I will grade them. All right. So far, yes. The reason I have a lot of posted because they are available. But most of them are optional. In the syllabus or the email, I said you only need to submit 4 worksheets, right? Yeah, you only 4 of those worksheets are mandatory, and all others are optional. Am I clear? Did I answer your question? Okay, awesome, perfect. Thank you. Yeah. Okay, so let's go back. This is the pattern again, right? Yeah. Do you see what is it? Times 5, right? What is 3,125 times 5? So 5 is 5 to the power of 0. Oh, sorry, my bad. 5 is 5 to the power of 1. 25 is 25 is the square of 5. 125 is the cube of 5. 625 is fourth power of 5. 3,125 is fifth power of 5. So this is you can see this sequence as geometric because the element is 5 times of the element in front of it. So times 5 times 5 times 5. So 3,125 times 5 gives us 15,625. 15,625. Pattern again, yeah. So 1, 2, 1, 8. So you know what? I'm going to ignore those ones. I'm gonna ignore those ones. Oops. Yeah. So I only look at, because it's alternating, right? The pattern obviously is alternating. I only look at 2, 8, 32. Yeah. 2 is 2 to the power times 2 times 4 gives us 8. 8 times 4 gives us 32. So the pattern is multiplied by 4, right? Yeah. What is 32 times 4? 128. Okay? Yeah, I have a question here. What's the element behind 128? Yeah, after 128. Huh? What's the number next to 128? In a sequence. In this sequence. Yeah, is 1. Yeah, is 1. Yeah, exactly. Thank you. We have is alternating, right? Yeah. And then 500. And then 512, right? So it is 1. Yeah. So our answer is asking the next number after 1, so it's 128. Very good. Pattern again. So all the numbers elements in the sequence are fractions with numerator 1. That's very obvious. So we focus on the denominators. 9, 13, 14, 21, 25. As you can see, is adding, right? Yeah. You add a 4 to 9, you get a 13. You add a 4 to 13, you get a 17. You add a 4 to 17, you get a 21. You add a 4 to 21, you get a 25. So the next number, numerator is 1, with all the same with all other elements. Denominator, we are going to add 4 to 25. Do you see is going to be 29? Right? You see that, right? Or you can watch the video later. It's posted in Blackboard. And this is a pattern again. Yeah. Question, are we doing induction or deduction? when we try to identify the numbers in a sequence based on the given first a few elements, are we doing induction or deduction? Yeah, we're doing induction. Thank you, Lane. Exactly. All right, so let's see how do we applying the inductive reasoning to find the pattern and determine the next number in a sequence. So I have a 1. 1 can be written as 1 over 1, by the way. So all the elements would be a fraction with numerator 1. Yeah, the first number is a whole number, but you can see that as a fraction. 1 can be written as 1 over 1. So we focus on the denominator again. So the first denominator is 1. Second denominator is 5. Third denominator is 25. Fourth denominator is 125. So what do you think? The denominator is multiplied by 5, right? Yeah, from 1 to 5 times 5, from 5 to 25 times 5, times 25 by 5, 125, and times 125 by 5, we have 625. So that should be the next element. Yeah, do not get confused by the first element. Try to write all the elements in the same form or format. Even the first element is not a fraction, but we could totally write that number 1 as 1 over 1. Then it's consistent with all other elements. Pattern again, from 5 to 8, 8 to 13. This is a good question. I'm going to copy paste. The difference has a pattern. Yeah. The difference has a pattern. It just doesn't let me to snip. Let me see if I can just copy paste this way. Okay, can you help me just tell me what is the next element? So we start from what? The sequence is. Anyone can unmute your thing?
You have a trip.
5, 8, 13, 20. 5, 8, 13, 20. 29, 40. And we're trying to determine what's the next element, right? Yeah. Look at the pattern. We consider the difference between any two consecutive elements in the sequence. The difference between 5 and 8 is 3. Difference between 8 and 13 is 5. Difference between 13 and 20 is 7. Difference between 20 and 29 is 9. Difference between 29 and 40 is 11. So look at the difference. Look at the pattern of difference. 3, 5, 7, 9, 11. Yeah, does that, tell you, like indicate anything? They are odd numbers, right? They are odd numbers. Yeah, 3, 5, 7, 9, 11. What's the next odd number? 13, right? Yeah, so we should add 13 on top of 40. And we should have 53 as the next number in the sequence. Do you agree? You have 53? Okay, awesome. Okay, so this is not exactly the same type of problem that we have done the beginning of today, right? I would say you can try on your own. Okay, yeah. So actually the beginning is the induction, and the proof, only the proof part is a deduction. And number 20, same. 21. And let's see this one. Use inductive reasoning to predict the next line in the sequence of computations. Then use a calculator or perform the arithmetic by hand to determine whether your conjecture is correct. The conjecture of a inductive reasoning is not certain. Let's see what we have in this case. So we have 11 times 9091 gives us that. 22 times that gives that. 33 times that. So what do you think about? The next line would be what? 55, right? And equals what? As you can see, 1, 2, 3, 4, 5, right? 505. Very interesting. It has a pattern. Not always, but for that. Okay. So study the pattern in these examples. Select the equation that describes the pattern. Select the correct equation. Let's see, study the pattern in these examples. Okay, so, okay, so those are the examples. Yeah, we are doing induction. So a to the power of third. And you might wonder, what is that? It's just the operation. You know, even we are not mathematician, like famous mathematician, we could define our own operations. This is one operation. Let's see the definition of the operation or the pattern. A to the power third times a to the well, not times, like operate with a to the power second. We get a power of 8, and this one is 4, 3 gives us 14. 5, 7 gives us 37. Lucky us, is multiple choice question actually, so it's gonna be easier. Let's see if it's this pattern. 3 times 2, 6. 6 plus 2 is 8. 4 times 2 is 8. 8 plus 3 is 11. No, so A is wrong. This one doesn't work. Let's see this one. So the first exponent add twice, plus twice of the second exponent. So 3 plus 4. 3, what happened? 3 plus 4. No, is incorrect. 3 plus 4 is 7, not 8. So this is incorrect as well. And let's see this one. The exponent is adding together and the plus 4. So 3 plus 2 is 5. 5 plus 4 is 9, not 8. So out. This one is incorrect. The last one, multiply the two exponents and then add 2. Multiply 3 and 2, 6. Plus 2 is 8. Multiply 4 and 3, 12. 12 plus 2, 14. Multiply 5 and 7, 35 plus 2, 37. Yes, the last one is. It might take a little bit of time. The design of the question is a little bit, it's a good design. It's a good, very well designed problem. Question about this problem, please. Do you see what I'm talking about this problem? Oh, I wish I could see you. It's really weird. Or at least if I can hear you. I don't mind noise, background noise. Okay, perfect. So check. Choose which reasoning process is shown in the following example. Explain. We did this one. in the video actually. I did this one in the video. So an HMO does a follow-up study on 1,106 randomly selected patients given a flu shot. None of these people became seriously ill with the flu. The study concludes that all the patients be urged to get a flu shot in order to prevent a serious case of the flu. This is from specific to general. From 1,106 specific cases to make a conclusion about all the patients. So this is from specific to general. So it's induction, right? Induction. So A or D. Yeah, because a general conclusion is drawn based on specific observations. Let's look at the D. It is induction because the flu is an epidemic. If someone does not take the flu shot, there's a great possibility for it's just the A. Yeah, D is too complicated. We are talking about reasoning, so just the A. How do we evaluate the reasoning? Good or bad, strong or weak, depends on the representativeness of the sample. The 1,100 people, is that a good sample? Are they representative or not? Okay, this one, the course policy states. This is an example of, what do you think? The course policy states, work turned in late will be marked down a grade. I turned in my report a day late, so it was marked from B to C. From general to specific. The specific conclusion. My report was your report was a day late, was arrived from one or more general statements. Yeah. From all the policy applies to all. So the policy applies to you. From general to specific. Okay. This is an example of deductive, the specific conclusion. Oh, my bad. The report is marked down from B to C was arrived at from one or more general statements. Conclusion, not condition. Conclusion. Marked down from one, the consequence, right? Turning late. Okay. We should be able to finish today this one. Choose the correct answer. The statement is, I use deductive reasoning to draw conclusions that are not certain but likely. I use deductive reasoning to draw conclusions that no. The statement does not make sense. Deductive reasoning provides conclusions. Deductive reasoning only provides true conclusions if the conclusion is also true by inductive reasoning. Deductive reasoning always provides certain conclusions. Deductive reasoning always provides certain conclusions. Is either valid or invalid. If it's valid, it's either sound or valid but not sound. It is certain. Last one. Determine whether the following statement, okay. Additional information may strengthen or weaken the probability of some inductive arguments. Yeah, I think so. Yeah, the conclusion from inductive reasoning is called a conjecture, right? Yeah, if you have a counterexample, you can just beat it up. You can just say disprove it. Yeah, the statement makes sense. One can never be absolutely certain that the conclusions of analysis are true, because an inductive is not yet an inductive conclusion. Makes sense because one can never be absolutely certain. Yeah. Okay, let's see. Yeah, it's correct. Okay, so only 2 questions we didn't cover, but the first question of today's class is similar with those 2 questions. All right, guys, that's for today. I hope it helps, and we'll do as much as possible. This will not. Okay, thank you, Ashley. Yeah, you still have to practice yourself, of course, because my numbers is probably different from yours. Okay. All right, I'll see you tomorrow, guys. If you have any questions, feel free to email me. Have a good evening. Bye-bye.